Hi there, welcome to section 6.3, which is on ratios, proportions, percents, and scientific notation. This is a big lesson today. There's a lot of different concepts. So let's just jump in. We're going to start by talking about ratios. So here's some everyday life examples of ratios that you might see. So for example, WCC suggests that the ratio of credit hours to time student study outside of class should be 1 to 3. Let's talk about what this means. So the way that we write a ratio, the order that we write those numbers matters greatly. So when we say the ratio of credit hours to time student should study, the 2 is kind of like the colon. The credit hours go with the first number, and the time student should study go with the second. So it means for every 1 credit hour of class, there should be 3 hours studying outside of class. Now, with a ratio, it doesn't mean that students will only take 1 credit hour. This can apply to any amount of credit hours. So let's say, for instance, a student signs up for 6 credit hours. So we basically just have to keep with the same ratio. For every 1 credits, there are 3 hours study time. So if there are 6 credits, then there would be 18 hours of study time, which yes, that seems like a lot, but that's actually what is suggested. So you can always write these ratios as a fraction, like 1 to 3. So that way you can write this one 6 over 18. And you can see a little bit easier that way that we're just multiplying both those numbers by 6. So another example, the WCC pharmacy program, I just looked this up on our website. They advertise that they have a standard ratio of lab to classroom instruction. They don't tell you what it is, but they have this ratio that they use as a guide. The faculty-student ratio at U of M Ann Arbor is 1 to 16. So because we said faculty first and student second, that means faculty, that's your 1, and student, so for every 1 or for every 16 students, there's 1 faculty member. The student faculty ratio at WCC, so I switched it up a little bit, is 26 to 1, meaning student is first. So for every 26 students, there's 1 faculty member. So this basically says that, U of M has smaller class sizes, usually, or they have more faculty per student. So in English, the word per means for every, and it indicates a ratio. So for example, like when you see 35 miles per gallon of gas for every. So 35 miles, you can drive 35 miles for every gallon of gas. And a ratio is just an ordered pair of numbers that you can write like A colon B, or you can write it as a fraction, A over B. Now the definition states that B cannot be 0. So think about why B might not be 0, particularly when written like this. You can see it a little bit better. The denominator of a fraction can never be 0. So that's why we add this note here. But in real life, it's possible for B to be 0. So for example, like if you were watching a basketball team throughout the season and they said that their ratio of wins to losses was 5-0, that would certainly be reasonable because that would be 5 wins and 0 losses, and that would make sense. But mathematically, technically, since a ratio can be written as a fraction, we add that note that B can't be 0. Ratios can also be reduced. A ratio, again, is just like a fraction. So for example, let's say you had a ratio of 3 to 6, you could divide both those numbers by 2, just like if it were written like this, and you would end up getting not by 2. That wouldn't make much sense. Divide both of them by 3. 3 divided by 3 is 1. 6 divided by 3 is 2. That's also the same as 1/2. So just keep that in mind. So there are different types of ratios that we're going to talk about. So let's talk about part to part, and then we'll also talk about part to whole. So part to part, example, there are 13 girls and 15 boys, maybe in a classroom. So you could say that the ratio of girls to boys is 13 to 15. So 13 girls, 15 boys. Neither one of those numbers is talking about the whole class. Now you could add up those numbers to figure out how many people are in the class. So you get 20 people in the entire class. Okay, and that brings us down to this next part. So you can also write a ratio, a part to whole ratio or whole to part, where maybe you want to write a ratio of girls to total students. So you say the ratio of girls to total students is 13 to 28. So you really just have to pay attention to what's being, like what the directions or description is referring to. So I have to pay attention to those words. So let's talk about how we can simplify some ratios. So example 1 says in class 1, the ratio of girls to boys is 8 to 6. So I'm just going to write class 1. We've got girls to boys. The ratio is 8 to 6. In class 2, so I'm going to write over here, class 2, the ratio is 4 to 3, and we're going to still assume that's girls to boys. Suppose that each class has 28 students. Do these ratios represent the same relative amounts? Well, let's draw a picture. So if class 1 has 8 girls for every 6 boys, what we can do is we can write it, draw a diagram like this, where we say 8 girls, 1, 2, 3, 4, 5, 6, 7, 8, 6 boys. Now, 8 plus 6 is 14, so there's 14 kids there. Now, it says there's 28 students in the class, so I need to keep going, and I'm going to do that again. So 8 girls, 6 boys, and we've got another 14 for a total of 28. So it looks like there's 16 girls and 12 boys in the class. So 16 girls, 12 boys. And remember, we can always reduce this. So if you look at 16/12 as a fraction, 16 over 12, if you divide those both by 2, you end up getting 8 over 6, which is the way that our initial ratio is written. So then with class 2, I'm going to actually move this so I have a little bit more room here. So class 2, our ratio is 4 to 3, and that's girls to boys. We're going to build it up the same way. So 4 girls, 3 boys. Okay, we're only at 7 there, so we need some more kids. So 4 girls, 3 boys. Now we're at another 7, so that's 14. Another 4 girls, 3 boys, that's 7. Now we're at 21. That's another 7, so 7 times 4 is 28 total. So now we have our class. Now let's look at the individual amounts of girls and boys. So it looks like we've got 4, 8, 12, 16 girls. So 16 girls in class 2, 3, 6, 9, 12, 12 boys. And if we look, that's the same exact amount of girls and boys that we had in class 1. So we would say, yes, they do. So just like fractions, it's possible to have different ratios that look different, but when you reduce them, they end up being the same thing. And so let's just finally, you know what, I'm going to erase this up top here so I have a little bit more room. Let's look at these ratios side by side real quick before we move on. If you look at them like this, just like fractions, we can say, well, how do you relate 8 to 4? Well, 8 divided by 2 is 4. If I do the same thing to 6 divided by 2, I get 3. So we basically, you could also write it as a fraction, we essentially reduced the first ratio to make the second. So they mean the exact same thing. So let's do the U-try. So this would be a great time to pause the video and try these on your own. So determine if the following ratios are equal. So with these, you could draw a picture like I did. You could keep them as ratios and just say to yourself, well, how do I go from 3 to 15? I could times 5. How do you go from 4 to 22? If I follow that same rule of times 5, I shouldn't get 22, I should get 20. So I would say no, they're not equal. The other thing you could do is write them as a fraction. You could divide these in your calculator and get a decimal for both. You'll see that they're different decimals. You could also do the same method that I did over there where you do times 5 and realize, oh, that doesn't work, so you say no on that one. For this one, 11 times 6 is 66. 6 times 6 is 36. So we would say yes, they are the same. And just like fractions, let me just be real clear. If you're comparing these, you have to use multiplication. You cannot use addition. So for example, you couldn't say 6 plus 30 is 36. That's true. But if you look up here, 11 plus 30, that rule doesn't hold true. So the way that we reduce fractions, convert fractions, is we use multiplication or division. So make sure you ask yourself, how do I multiply or divide to get to the next number? So the second part that we're going to talk about is a rate, because ratios can definitely represent a rate, and I'm sure you've seen this many times during your life. For example, miles per gallon or price per ounce. So when you have a ratio where one measure is being compared to a different measure, then we say that this is a rate. So example 2, determine the quantities or measures compared in each of the following statements, and state them as a rate, state the rate as a ratio. So Andrew gets 25 miles per gallon with his new car. So if I were to write this as a ratio, it would be 25 miles per 1, and actually, you know what, let me write the units. 25 miles per 1 gallon of gas. The box of Cheerios was unit priced at 21 cents per ounce. So 21 cents per 1 ounce. And you may have noticed a lot of grocery stores now, when you're shopping, if you look at the price tag, like I know for example, like in Kroger and the Meijer by me, they both have, if you look at the prices of all the items, like if this is the ticket, there's usually like a little number in the, I think it's the lower right hand corner or left, I can't remember, but maybe, you know, you're looking at Cheerios and you see this say 0.21. That's awesome because it tells you the price per ounce, and that's what you want to look at, because it makes it's really confusing when you look at the main price. Like if you look at the total price and see, oh, $3.99, if you want to compare and try to get the best value, it's hard to look at the prices, because there might be a box of cereal that's $5.25, more money, but maybe it's a better value. Or there are times where the more expensive item isn't the better value. So what you want to do is you want to look at the unit price, and whichever one has the lower unit price, you know that that one is cheaper. And that way you don't even have to do any math. You can just look at that, which is helpful. So the third way that we can use ratios is through a proportion. So a proportion is a statement of equality that two given ratios, which in this case just fractions, are equal. So for example, 1/2 is the same thing as 2/4. This right here is called a proportion. The whole thing, 1/2 equals 2/4 is a proportion. And if they are equal, then what you can do is you can cross multiply, which means you multiply what's on the diagonal. So A times D equals B times C. And that's how, and you can look up here with my example, 1 times 4 equals 2 times 2. 1 times 4 is 4, 2 times 2 is 4, and so you can see that that works out. And that allows us to solve equations. So let's use that in these following examples. So example 3, Adam's school orders 3, should say apostrophe, Adam's school orders 3 cartons of chocolate milk for every, so there's your rate, so 3 cartons of chocolate milk for every 7 students. Now, I don't always know that I'm going to want it in a fraction like this, but I like to write it as I'm reading it, as it helps me organize my thoughts. If there are 581 students in the school, how many cartons of chocolate milk should be ordered? So we've got milk on the top and we've got students on the bottom. So 581 students can go right down here. So when we make a proportion, what we want to do is we want to make sure that the same units are lined up. So if we put chocolate milk on the top, then we need to be consistent. If we put students on the bottom, then we have to be consistent. So it says how many cartons of chocolate milk should be ordered. Well, we're going to put an X here. We're going to say X equals the number of cartons ordered for the school. That's what we're trying to find out. So this fraction represents the school. How many cartons of milk should I order for 581 students? There are 3 cartons of chocolate milk for every 7 students in the school. And then what I can do is I can cross multiply. So I can multiply what's on the diagonal. So 3 times 581 equals 7 times X. So 3 times 581 is 1,743 equals 7X, and then divide both sides by 7, and you end up getting 249. And then if you're wondering at the end, I know sometimes this happens to me where I'm just like, oh, I got my answer. What does that mean? Well, go up to your ratio, and hopefully you labeled it. I labeled it here. X equals number of cartons ordered for the school. So that way you can write, okay, that's cartons. And then with your calculator, let me just pull up my calculator real quick. We can just do a quick check. So 3 divided by 7, I'm going to divide that first fraction. I get a decimal, 0.428, and then it continues. But just remember 0.428. And then I'm going to do, let me move it over here so we can see, 249. So 249 divided by 581, and I get that same decimal, which is awesome. That's the best way to check your work. So let's look at example 4. So a recipe calls for 1 cup of mix, 1 cup of milk, and the whites from 4 eggs, 3 teaspoons of oil. If this recipe serves 6 people, how many eggs are needed to make enough for 15 people? This one can be tricky because they give you a lot of information that you don't need. So the mix, the milk, the oil is actually unnecessary because, you know, we're just wanting to know how many eggs. So how many eggs are needed for 15 people? We're just going to say X equals the number of eggs needed. And I'm going to want to write a ratio that has to do with eggs. So I'm going to go to the part that talks about the eggs. So we want the whites from 4 eggs. Okay, so I know that I need 4 eggs for every, that recipe serves 6. So 4 eggs for 6 people. And then I'm going to be consistent. I decided to put eggs on top. So I'm going to keep eggs on top the whole time, and I'm going to keep people on the bottom the whole time. And I don't have to do it this way. I could have flipped it around and done people on the top, eggs on the bottom. It doesn't matter as long as you're consistent. So I want to know how many eggs do I need for 15 people. This is a great problem because if you do any type of cooking, you probably run into this all the time. And now we're lucky we've got websites where we can just change the number of people, but this comes in handy. So 15 people. Now I cross multiply. So 4 times 15 equals 6 times X. So 4 times 15 is 60 equals 6X. Divide both sides by 6 and you get 10 equals X. So we need 10 eggs for 15 people. And then double check, take that 10 and plug it in. So let's look and see, is 4 6 the same thing as 10 over 15? And this one, what we could do is we could, if you wanted to, you could pull up your calculator again. So 4 6, you get 0.6 repeating, and then 10 over 15, and you get 0.6 repeating. So we know we got the right answer. Okay, so example 5. I'm going to erase some of this so I can see it. If your car averages 29 miles per gallon, how many gallons should you expect to buy for a 609-mile trip? This is also a great one for real life. So I'm just going to write down my rate. So 29 miles per gallon means for 1 gallon. So 29 miles for every 1 gallon. 609 mile trip. So I'm going to put miles on the top since I put it on the top over here. So for 609 mile trip, I'm going to say how many gallons do I need? So gallons is on the bottom, miles is on the top. And then I cross multiply. 29 times x equals 1 times 609. And then I'm going to divide both sides by 29. And I'm left with 21 gallons of gas. And then we can do the same thing. So 29 divided by 1 is 29. And then you can take your calculator and do 609 divided by, 609 divided by 21. And we're left with, did too many, that doesn't make sense. 609, one more time. And there we go, we get 29, so that confirms that we did that one right. And then last, we're going to do example 6. So two neighbors are just trying to decide whether their property taxes were fair. The assessed value of one house was $175,800 and its tax bill was $2,777.64. So I'm going to write that as a ratio. So we've got the assessed value. So we put the value, and I'm going to compare that to the tax. The other house had a tax bill of $3,502.85 and was assessed at $189,300. Were the two houses taxed at the same rate? So there are a lot of different ways you could do this problem. One way is to set this equal, and we're questioning whether or not they're equal, and we could test that by cross multiplying. So if you multiply those together, we get 615 million and some change. And then I'm going to multiply these two numbers, and I get this number. And I see that they are not equal. So we can say, no, they're not taxed at the same rate. The other thing you can do is you can divide these two numbers. You can divide the value by the tax and compare that to the value for the tax. One downside is you do have to do, I would say, a little bit more thinking if you do it that way. So 175,800 divided by 2,777.64 equals, so if you divide those, and I'm just going to erase this real quick so I can see. Okay, let me get my calculator back. Okay, I get 60, I'm going to round it to 2 decimal places, so $63 and approximately 29 cents. 63.29, and then let me do the other two. So other two numbers. So then I do 189,300 divided by 3502.85, and I get 54.04. So one question you could ask, well, which one is better? And this is where you got to be careful, because sometimes, well, let's just back up. So let me back up. So let me talk about what this number means. So if you reduce this, let's put this over 1. What this means is that for every $63.29 that the house is worth, you have to pay $1 in tax, whereas for this house, for every $54.04 that the house is worth, you have to pay $1 in tax. So a lot of people, like I know when I do this in class, I have a lot of students say, if I ask them the question, well, which one's the better deal? And a lot of people say, oh yeah, this house, this is better deal. And it's actually not the better deal. And the reason is because the consumer is paying $1 for every $54 it's assessed, so it's paying that money more frequently, whereas this person can actually have more, their house is worth more for every dollar that they end up paying. So the bottom is what you pay, and the top is what your house is worth or assessed at. So this house is actually a better deal in terms of the taxes. So let's jump into percents. So there are many, many examples. I'm sure you see them all the time of percents. The stock average, we see percents with sports all the time. Some sales, the land prices or housing market is either up or down, and usually it's expressed in a percent. The word percent literally means per is for every, so we already talked about that, and then cent means 100. So think like century, 100 years, or cent like penny. There are 100 pennies in a dollar, so cent, the root of cent is 100. So for every 100. So for example, if you get a 75% on a test, it's like saying you got 75 out of 100 correct. And we know that that doesn't mean if you get a 75% on a test, it doesn't mean that every single test has 100 questions and you got 75. It's just the relationship between those two numbers. So the ratio is 75 over 100, but you could actually have any amount of questions on the test. So let's talk about how to do some converting because this is handy. So the first one we're going to do is convert percents to fractions. Oh, it looks like I'm freezing up here. So to convert a percent to a fraction, one way you can do it is you could do with a decimal square, and this is a great way to do to teach kids how to do this. So 63% literally means 63 per 100. So the decimal there is 63 out of 100. You could also draw it on a picture. 2, 3, 4, 5, 6. So you've got 6 there. And then an additional 3. 63 out of 100. 12% to a fraction. 12 per cent. So 12 out of 100. And that would be 12 of these squares out of 100. If you can reduce, it's preferred. So 12 over 100, we could reduce those both by 2, and we could get 6 over 50 there. We could reduce them by 2 again, and we get 3 over 25. So that's another way to write it. But both are good, 12 over 100 or 3 over 25. If you're given a decimal or a percent that has a decimal, so 1.35% to a fraction, you still can take 1.35 and put it over 100. So 1.35 per every 100, but you don't want to leave a decimal in a fraction. So one way that you can get rid of it is to take that decimal and move it 2 spots to the right, and if you do that to the top, you also have to do it to the bottom and put placeholder zeros. And so what this now becomes is it becomes 135 over 10,000. And then you actually have to reduce that. So if we could reduce that by 5. If we divide those both by 5, we end up getting 27 over 2,000. So that would be the fraction. And then how many parts shaded out of how many? Well, it depends. You could write 1.35 out of 100. That'd be the simplest way. You could also do, and that's really with our decimal squares, they're always out of 100. Now you could also say, you could draw a picture of 27 over 2,000, which is true, or 135 over 10,000. So there's many different ways you could write that last part. So 16.5% means 16.5 for every 100, or 16.5 parts shaded out of 100. And then just like before, we want to move that decimal out of the number, and I'm going to put a placeholder 0 on the bottom. So the fraction is going to be 165 over 1,000, and then we want to reduce that. So we could reduce that. Both of these are divisible by let's see, maybe 5. Yep, if we divide that, we end up getting 33 out of 200. Okay, and then next, case 2, so percents to decimals. So how do you go from percent to decimal? So 63% would be 63 out of 100, which means that it's 63 hundredths, which means 0.63. The other thing that you can do is you can remember the rule that when you have a percentage, if you want to convert to a decimal, all you have to do is take the decimal place, which is at the end of the number if you don't see it, and move it 2 spots left to give you 0.63. So 12% would be 12 parts shaded out of 100. And then you can move that decimal 2 spots left for 0.12. 1.35% to a decimal is 1.35 shaded out of 100. And then we could take that decimal and go 2 spots to the left. You're going to need a placeholder 0 there. So 0.0135. And then 305%. So what does that mean? It means 305 parts shaded out of 100, which means you're going to have multiple boxes. So you've got 100, 200, 300, and then you'd have 1, 2, 3, 4, 5 of those little boxes. So it looked like this. You could take the decimal here and move it 2 spots to the left. So the decimal for that would be 3.05, which is also what this picture represents, 3 and then 0.05 there. So case 3, now let's go decimal to percentage. So this is backwards, the opposite of what we just did. So we moved our decimal left 2 places to go from percent to decimal. Now we can go backwards, so to the right 2 spots. So 0.48 or 0.58 is 58 parts shaded out of 100, and the decimal is, or the percentage, sorry, would just be 58%. And then I'll go back to my blue. Same thing here, 0.03 would be 0.03 parts shaded out of 100. And then we move the decimal 2 spots to the right, and we end up getting 3% there. Oh, and you know what? That's not right. So 3%, it's not 0.03%, it is 3%. So if it's 3%, then 3 parts out of 100. And same thing here, this 1.5, that's not a percentage, so I'm going to wait to fill in my shading part. So 1.5 to a percent would be 2 spots to the right, so it would be 150%, which means I'm going to shade 150 parts out of 100, which I know sounds weird because it's more than 100, but it means I'd shade 100 and then 50, which also represents 1.5. And then 0.005, we're going to go 2 spots to the right, so it'd be 0.5%. So I would shade 0.5 parts for every 100 for that one. Okay, so this next part, we're going to get into some harder problems. We're going to get into some percent story problems, and there's definitely many ways that you could approach these. I'm going to show you a couple, and they by all means not the only methods that you can use, but just something to think about. I want to give you kind of 2 different, well, you know what, even 3. So let's do this. One method is, you can remember, is over of equals percent over 100. That's one method of doing it. And so I'm going to actually take these first 2 examples, and I'll do it like that. So is over of equals percent over 100. So what this means is the number, look for the words is and of in the problem, and that'll help you figure out where to put them. So 0.5%, so my percent is 0.5 out of 100. Of what number? That's the number. I don't know what that is. It's asking. So the of number is going to be X. Is 78.4. So I'm going to put that where the is would be. Is 78.4 over of, we don't know, equals percent over 100. And then what I can do is I could cross multiply. So I multiply those 2 together, and I end up getting 0.5x equals 100 times 78.4. So 7840, divide both sides by 0.5, and I end up getting 15,680. definitely take your calculator and do 78.4 divided by 15,680 and make sure you get what you would get 5 over 100, which is 0.5. So just double check. Let's do this next one, same method. So 147 is, that's my is number, so is over of 42%, so 42 is my percent over 100, of what number? So I don't know what of is, so I put the x down there, and then I cross multiply. 147 times 100 equals 42x, and then I divide both sides by 42, and I end up getting 350. Okay, so this way I feel like is the benefit of it, it's got a nice ring to it. Is over of equals percent over 100. It's something that I learned in middle school and I've remembered ever since, so it's catchy. The downside is I don't think it's creating a ton of critical thinking, but that could be okay. We are doing a proportion, which is good. So another method that I really like is called the fuel gauge. And this is one that I never used as a student, but I did it, I learned this during student teaching when I was student teaching in an 8th grade classroom. And man, it was amazing to see how this really clicked for a lot of the kids. So the way this works is you draw a rectangle. You can do it horizontal or vertical, it doesn't really matter. And the idea here is you think of a fuel gauge like as it being filled up by a certain amount. And what you can do is you can put 100% at the bottom, and then you put the percentage that you're given in the problem to match up with where the rectangle goes, and then the numbers are going to go on the top. So your is number goes above the percentage. Oh, but it looks like I'm freezing again. Let me see if I can fix this. Okay, there we go. Your is number goes on the top, and your of, or your total of, the word of is referring to the total value. So the total value goes with the 100%, and the one that's the portion or the fraction goes with the percent that's given in the problem. So this is how it works. So for this one down here, I'm going to draw a fuel gauge, and I'm going to look for the percentage first. Oh, and you know what? I'm actually going to I take that back. I'm going to come back to this one. Let me do a simpler one. Since that percentage is over 100, I think it'd make more sense just for our first example to use a percentage that's less than 100. And then we'll do one later with the fuel gauge that's more, so you can see that. So 63%. So I'm going to do a fuel gauge, and I'm going to draw a line where I think 63% would be. So it's more than half. And so I'm going to write 63%. That represents 63. 100% would be completely full. It's not completely full. And then of 90. So my of number, 90 is the total. So that goes with the 100%. So if I were all filled up, 90 would be the number that represents that. And then is what number? So that's going to be my x. And then I write a proportion. So x, I can do this many different ways. I can say x over 63 equals 90 over 100. You can also do 63 over 100 equals x over 90, and then that matches up with what we did over there. That will work too. You just have to be consistent. So you're going to cross multiply. Okay, so x times 100 equals 63 times 90. And then divide both sides by 100, and then you end up getting 56.7. And then the great thing is you can actually come up to your picture now, and you can write in your answer. So 56.7. Double check. You can divide these together and divide these. You should get the same number, but ask yourself, does this make sense? If 90 is all the way filled up, is 56.7 about 63%? It's a really great visual to see, to just eyeball whether or not your answer makes sense. And then let's do this next one. So 65 is what percent of 104? So if we know 104 is all filled up, 65 is going to be like right there. And it doesn't have to be to scale. What percent? We don't know the percentage that 65 is, but we can write 100% there. And then we can do 65 over x equals 104 over 100, and then just cross multiply. 65 times 100 equals 104x. Divide by both sides by 104, and then we end up getting 62.5. And that's a percentage because the bottom x, that's where the percentages go. Okay, and then let's do one more like that. So I'm going to draw my rectangle. 31.3%, so that's like a third of the way. So I'll do my percentage of 1200. So my of number, total number goes at the top, is what number? We don't know, but we're going to find out. And then 100% goes there. So x over 31.3 equals 1200 divided by 100. And then you cross multiply, and then you get 375.6. And then we can come up and write that number right on top instead of x, 375.6, and ask yourself, does that make sense? Does 375.6, does that seem about a third of 1200? And it does. A third of 1200 would be 400. So that's a good way to just eyeball your answer. And then the other, I'm just going to show you one other method. So just scrolling up at the top here, I wrote my two methods. Method 3, and I'm not going to put a whole lot of emphasis on this only because in elementary school you don't spend a whole lot of time writing equations, and students will get a lot more practice in algebra doing that. But you can write an equation for these also. So let's do that with the very last one. So is in math oftentimes means equals, and of means times. So if you want to translate this, 3,648 is 128%. So let's just write that as a decimal. We're going to move the decimal 2 spots to the left, 1.28 of what number? And then what we can do is we can just solve the equation. So we can divide both sides by 1.28, and then we end up getting 2,850. So again, I'm not going to put a whole lot of emphasis on that, but I just wanted to show you how you could do this a bunch of different ways. And I would encourage you to have an open mind and try to learn all of them. But if there's one that really speaks to you, I think it's totally okay to just practice that one and use that one more than the others. So let's do some examples. So a car was purchased for $13,000 with a 20% down payment. How much was the down payment? So what we could do here, if you wanted to use, I've got the decimal square that you can use as a fuel gauge if you want. And the nice thing about this is we can make it a little bit more accurate. So 20%, I could put right here, not right there, right here. So that represents 20% out of 100%, okay? And then is over of, you can think of those on the top. So a car was purchased for $13,000 with a 20% down payment. How much was, which is the same thing as is, it's just past tense, the down payment. So we don't know what the down payment is, that goes with the 20%, but I do know that total the car was $13,000. So this is how I can do it, and then I can make my proportion from there. So x over 20 equals 13,000 over 100, and then I can cross multiply. X times 100 equals 20 times 13,000. And then you can multiply, so 100x equals 26. And then I'm just doing 2 times 13, 26, and then 1, 2, 3, 4 zeros. So I've got 4 zeros. And then I'm going to divide both sides by 100. And I don't need a calculator for this. I can just cross off the zeros, and I end up getting 2,600. Okay. You could also just take 20% of 1,300 by doing an equation, or just saying 20% as a decimal of 1,300, and that would also give you 2,600. Yes, that's faster, but again, the goal is not always fast, it's understanding. So I think it's good to be open to the picture in other ways if that makes sense for some people. Okay, I'm just going to erase this so that I can see this next one. So 162 seniors, 90% of the senior class. So I'm just going to draw where 90 would be. So that'd be 90 of these squares. So 90% would be that, 100% would be all the way. 162 seniors, 90% of the senior class. So the 162 goes with the 90%. And then, it's hard to read this, 90% are going on the trip. How many seniors are they there? So I'm going to put an X there because I don't know the total. X goes with the total. So I'm going to write 162 over 90 equals X over 100. And then I'm going to cross multiply. So 16200 equals 90x. Divide both sides by 90, and I end up getting 180. And then ask yourself, does this make sense? So if I were to replace this x with 180, if 162 is 90%, does 180 seem reasonable for 100? And I think it does. It absolutely does. And then you could take your calculator also just to double check and do 162 divided by 90 in your calculator, and then take the 180 and replace x with it and divide by 100, and you should end up getting the same thing. Okay, so part C, Susan scored 48 points on a 60-point test. What percent did she get correct? So I'm sure many of you can just may realize that you could just do 48 divided by 60 and change that into a percentage. That would be a fast way. The other thing that you could do is you could draw a picture. You could say 48 and 60. We don't know what percentage, we're guessing. So I don't really know exactly how far to draw that fuel gauge, but I could just, for the picture's sake, just estimate. And you could set up a proportion, 48 over x equals 60 over 100, and then cross multiply, and then divide. And you end up getting 80%. And the nice thing about this way is you don't have to convert your decimal in the end, whereas here you do, and then you have to move it 2 spots left to get your 80, but either way works. D, Rochelle bought a dress whose original price was $125, but was discounted 10%. Okay, this is one where you really have to pay attention because it doesn't say that it was 10% of the original, it just says it was discounted 10%. So basically what that means is it means that, so if this is 100, if it was discounted 10%, that means 10% was taken off. That means she ended up paying 90%. So 10% discount is this red part. And so the original price was $125. What was the discounted price? So we can put an X there. So X, what is the price? The price goes on top compared to 90% if $125 is the 100% price. And then we can cross multiply. So 100 times X equals 90 times 125. And then if we cross multiply, there we end up getting $112.50. So the great thing about the picture for this one is we can really see visualize the discount, and that can help us get the 90. If we didn't have the picture, we could still do it, but we wouldn't have that visual there. And then the last one, we've got another discounted price. So a television set is put on sale at 28% off the regular price. So what I'm going to do is I'm going to think about where 100 would be, and I'm going to take off 28%. So here's 20, and then I'm going to do another 8. 1, 2, 3, 4, 5, 6, 7, 8. So that's 28, and this is going to be the discount. And so now we can fill in what we know. So the sale price is $379. So 379 is going to go there. What was the regular price? We don't know. What is the percentage? So if it's discounted 28%, then what is the percentage starting from 0 that would make meet that discount at 28%? And we can basically just take 100% minus 28% and we get 72%. So the person paid $379 at 72%. What is the price that would be equivalent to the 100%? And then we can cross multiply, divide both sides by 72. Looks like a 22. Let me just and then we end up getting $526.39. And then always ask yourself, does this make sense? So draw 526.39. And I think that does make sense because it's bigger than 379. Okay. And, by eyeballing it and just saying, oh, it's bigger, that's not a great check, but it's better than nothing. A lot of times that alone can help, find some mistakes. So we're going to jump to, just like we did in a lot of the other sections, some mental calculations. So one thing that's helpful is this chart that I made for you is a chart of some of the percentages that you might commonly see, and then the corresponding fraction. Sometimes it's easier to use a fraction, believe it or not, just depending on what problem you're doing. And then also remember that 10% is just so easy. And this is something to think about when you're giving tips. So let's say, for example, that you go out to dinner and your bill is $35.89. If you want to know what 10% is, all you have to do is move that decimal. So 10% is $3.589, and then we would just round, because if we're dealing with money, we would just say $3.59. And when I'm going out to eat, I don't even do it that much. I just say, oh, about $3.60, or I might just round even to 4. And then if you want a 20%, then all you have to do is double that. So if you want to round this to 4, then double would be about 8. Or if you wanted to actually add 359 and 359 to find the exact value for 20%, you could do that too, and you get $7.18. So just by moving the decimal, you can get 10%, and then by adding that, doubling that, you can get 20. So just a neat trick that's faster than pulling out your phone to do it on your phone calculator. So example 9. A store is having a sale and prices are being discounted 15, 20, and 25%. Calculate the amount of discount mentally. So, I'm just going to offer some suggestions. There's no right way here, but anytime I have to do 15%, what I do is I do 10% first. So 10% of 82 is just 8.2. And then if I do half of that, so half of 8.2 is 4.1. I just divided 8 and half is 4 and 2 and half is 1, so it's 4.1. So 10% plus 5% is going to be 15. So if this 8.2 is my 10%, then I add the 5% value, which is just half of that. Then I'm going to get my 15. So then I get 12.3 or $12.30. The next one, 20%. So I'm going to do 10% first. So 10% of 3140, I just move the decimal, is 3.140 or 3.14. And then if I want 20%, I just double it. So I add another 3.14 and I get 6.28. And so that would be 20. And then 25%, remember that 25% is just a quarter, or so you can multiply 30 by a quarter, or you can divide it by 4. So whatever is easiest. You can think about how do you make 4 groups within the 30, so you can divide it that way. Or you can also do 1/4 times 30 that way. either way. Now, the nice thing about the fractions is you could divide these both by 2. So 2 goes into 4 twice. It goes into 30 15 times. And then you just have to split 15 in half, which is $7.50. So you bring the numbers down a little bit that way. So example 10, these are similar. Calculate each percent by replacing the percent by a fraction. So 25% of 88, you could just say a quarter times 88. Divide 88 by 4, which is 22. 20% is the same thing as 1/5 times 55. 5 goes into 5 once. It goes into 55 11 times, so you end up just getting 11 for that one. 33 1/3%, that's just 1/3 times 45 over 1. 3 goes into 3 once. It goes into 45 15 times, so you end up getting 15. And then 75% is 3/4. Now, when I do this one in my head, I actually don't do the 3/4 part. I think to myself, well, 24 divided by 4 is 6. And then if I want 3 of those, 6 plus 6 plus 6, then I end up getting 18. That is simpler than visualizing this fraction in my head. But you can cross cancel and end up getting 3 times 6 is 18. So this next part, substitutions, calculate each percent mentally by replacing the percent by a sum or difference of 2 convenient percents. So what you could do for this one, so 95% of 200, what I would probably do is I'd probably think about what 5% is of 200 and then just take that off. So we know that 100% of 200 is just 200. So if I do 5% of 200, well, 10% is $20. So 5% is $10. That's what I would do in my head. And then I would just take off $10 and I'd get $190. And keep in mind that I feel like when I'm writing down the mental math and talking through it, sometimes it seems a lot more complicated. I think it's just one of those things where you just have to practice over and over and over again, and eventually it'll get simpler, but it really just does take a lot of practice. So 110%, what I would do, 100% is just the number itself. Find 10% of 430. So 10% of 430 is just 43. So then if you want 110%, you just take 43 or 430 plus 43, and then you get 473. And then last, 45%. So we know 50% is just half. So 50% of 18 is 9. And then what I could do is just find 5%. So 5%, well, 10% is $1.80, so 5% is going to be 90. And I know 10% is $1.80 just because I moved that decimal. So if 5% is 90 cents, then all I have to do is take, if I want 45%, is take the 50%, so 9, minus, so that's the 50% number, minus the 5% number, or 90 cents, and then I get $8.10. And then this next part, this is approximation. So compatible numbers, approximate, so we're not getting exact answers, each percent by replacing one or both numbers by compatible numbers. 34% of 62. There's not one right way to do this. The first thought that comes to my mind, 34% is really close to a third. Oh, I'm freezing up again. So I'm going to write 1/3 times a number that would be easily divisible by 3. So 62 is really close to 60. 3 goes into 60 20 times. That seems to me like it would be a reasonable approximation. 47% is really close to 50% or a half. So I would just do half, and then I'd round this number to a number that I could easily chop in half. So maybe 88 might be a good option. So 44. You could certainly say 90 and do half of 90. 8%, I would probably just round that to 10% of 65, which means I just move that decimal 1 in, and so that's 6.5 approximately. And then determine the approximate percents by replacing the numbers, numerators or denominators by compatible numbers. So if you want to make this easier math, how could you change these so that you could do it in your head? One thought is 15 over 60, because 15 goes into 60 4 times. You could, if that didn't come quickly, you could do 20 over 60, but keep in mind if you do 20 over 60, you get 1/3. So these are approximations. The 1/3 is going to be more off than the 1/4, but both are great approximations. This one, the 3, I know 3 goes into 24, but it doesn't go into 2490. So you could do 300 divided by 2400, or you could also do 300 divided by 2500. That would work too. So you could, and then you could simplify by just doing these and just do 3 over 24. You know, the hard thing though is if you're trying to find a percent there, 24 is really close to 25, so I'd actually just round that to 25. And then if we multiply that by 4, that gives us 100. I'm trying to make the denominator 100 because I need a percent. So I'm trying to do this without a calculator. And then 3 times 4 is 12. So it's about 12%. That's probably how I would do it if I didn't have a calculator. And then the last page, I know we've got this is jam-packed lesson here. We're kind of switching gears here. Let's talk about scientific notation. And this is going to be kind of a really quick, just touch base on this. Because this is, you know, I'm assuming that hopefully all of you have experienced scientific notation at some point. So scientific notation is a way for us to write really big and really small numbers. And for example, we could write a number like 33, this number right here. We could write 3.3 times 10 to the 16th power. And basically what this 16th power means is it's a 10 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 with 16 zeros. And the cool thing about zeros multiplying by factors of 10 is that it tells us to just move that decimal over to the right. So if we take this decimal and move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, then we get the number that we started with. So the number between 1 and 10, so this number is called the mantissa, and that has to be between 1 and 10. So that's why I decided to do 3.3. It would not have been okay for me to say, oh, 33 times 10 to the 15th, even though I would have gotten the same number in the end. 33 is not between 0 and 1 or 0 and 10. So we always say that the mantissa needs to be between 1 and 10. And then if you want a number that's smaller than 1, like this number right here, you can use a negative exponent. So this one, I would make the mantissa 1.2 because that number is between 1 and 10. And then times 10 to the negative, I would put my decimal between the 1 and 2 and count 1, 2, 3, 4, 5, 6, 7, 8, 9. And it's got to go to the left. So it's going to be -9. So negative exponents are small numbers. Positive exponents indicate big numbers. And then what we can do is we're going to do some computations with scientific notation. So compute each product and write in scientific notation. What we can do is we can use the commutative property, and remember with multiplication, like if you have 3 times 4 times 5 times 6, you can rewrite it any way you want in any order as long as you're multiplying everything together. So these are the same. So I'm going to actually rewrite this and multiply these numbers together and then these numbers with exponents. So 6.3 times 5.21, I'm going to use a calculator. I get 32.823. And then times 10, let's use our exponent rules. When we multiply, we add exponents. So 4 plus 3 is 7. Now, technically this is correct in a sense that we multiplied correctly, but remember the mantissa, which is this first number, has to be between 1 and 10, and this is not. So what we're going to do is we're going to compensate, and we're going to write this out. So if we have 32.823, if we have times 10 to the 7th, we'd go 1, 2, 3, 4, 5, 6, 7. So this is the number that we essentially got. We want the decimal to be here. So if we want it to be there, if we want it to be 3.2823, then that's going to have to go 1, 2, 3, 4, 5, 6, 7, 8. So it actually had to travel one more, and that's going to be our final answer. I know some students I've had in the past like to just sort of memorize, oh, if we move the decimal left one, then this is going to have to increase one. I like writing the whole number out. I think it makes more sense, but you can do whichever way makes more sense to you. And so same with this next one. You could pause the video and try it on your own if you wanted to. I'm going to multiply those two numbers in my calculator. Then I'm going to multiply these. I add exponents. So 4 plus negative 6 is negative 2. Then I'm going to write out the number. So negative 2 means move it 2 spots to the left. So 0.13485, and then for scientific notation, my mantissa needs to be between 0 and 1, or 1 and 10, sorry. So 1.3485 would be a great mantissa, the only one that would work for this, times 10, 2, and I'll just count. That would have to go 1 left, so I'm going to say times 10 to the negative 1 power. So I write out my number, I place the decimal where it should be, guaranteeing that my mantissa, which is this number, is between 1 and 10, and then I move the decimal where it needs to be, and I write the exponent accordingly. So this would be the answer. So I hope that made some sense. As always, if as you're trying your homework, if you have questions, don't hesitate to ask.